Around the year 2000, astronomers calculated the age of a nearby star called HD 140283 using standard stellar evolution models. The result was approximately 16 billion years. That number created an immediate problem. The universe, according to measurements of the cosmic microwave background, is 13.8 billion years old. A star cannot be older than the universe itself. The math does not work. The physics does not permit it. Yet there was the calculation, published, peer-reviewed, suggesting exactly that impossibility. The star became known as the Methuselah star, after the biblical figure said to have lived 969 years. And for over a decade, it sat as an unresolved paradox in the astronomical literature. This was not a fringe claim. HD 140283 is located about 190 to 200 light-years away in the constellation Libra. It is bright enough to be visible through binoculars under good conditions. Astronomers have known about it for more than a century because it moves across the sky at unusually high speed, roughly 800,000 miles per hour. That motion, combined with its trajectory, identifies it as a halo star, part of an ancient population that orbits the Milky Way in elongated paths rather than within the galactic disk. These halo stars are among the oldest in the galaxy, formed long before the disk itself took shape. HD 140283 is also metal-poor. In astronomical terms, metals means elements heavier than hydrogen and helium, iron, oxygen, carbon. The star has an iron content about 250 times lower than the Sun. That deficiency is a signature of extreme age. Heavy elements were not abundant in the early universe. They were forged inside stars and dispersed through supernova explosions over time. A star with very low metallicity likely formed early, before the galaxy had been enriched by many generations of stellar evolution. All of this pointed to HD 140283 being genuinely ancient. The question was, how ancient? The problem with dating stars is that they do not come with timestamps. Their ages must be inferred indirectly by comparing their observed properties, temperature, luminosity, radius, chemical composition, to theoretical models describing how stars evolve. One of the most critical inputs to this process is distance. A star's apparent brightness depends on how far away it is. To calculate its true intrinsic luminosity, you need an accurate distance. Even small errors in distance lead to errors in calculated luminosity, which then shift the star's position on stellar evolution tracks and produce incorrect age estimates. This was the core issue with HD 140283. In 2013, a team led by astronomer Howard Bond used the Hubble Space Telescope's fine guidance sensors to measure the star's parallax with unprecedented precision. Parallax is the apparent shift in a star's position when viewed from different points in Earth's orbit. By measuring that shift, astronomers can calculate distance through simple trigonometry. Bond's team analyzed data collected between 2003 and 2011 and determined that HD 140283 lies 190.1 light-years away. That refined distance measurement allowed them to recalculate the star's intrinsic brightness, which in turn allowed them to update its age estimate. The result: 114.5 billion years, plus or minus m.8 billion years. That uncertainty is the most important part. The fine 0.8 billion years is not a detail. It is the entire resolution to the paradox. If the star's true age is 14.5 minus m.8, that gives 13.7 billion years comfortably within the age of the universe. The paradox was not that the star was definitively older than the cosmos. The paradox was that early estimates, based on less precise distance measurements, produced ages that exceeded the universe's age. Better distance data resolved the conflict by narrowing the uncertainty and bringing the star's age into an acceptable range. But distance was not the only factor. The 2013 study also incorporated more detailed chemical abundance data. HD 140283 has an unusually high oxygen-to-iron ratio. Oxygen affects how energy flows through a star's interior, which in turn affects its evolutionary timeline. Including this abundance correction in the stellar models further refined the age estimate, bringing it down from the earlier, more problematic values. The combination of improved distance and better chemical modeling eliminated the apparent contradiction. Subsequent studies have pushed the refinement further. In 2018, the European Space Agency's Gaia mission released precise parallax measurements for stars across the Milky Way. Gaia's parallax for HD 140283 was slightly different from Hubble's, lower, implying the star is closer than previously thought. A closer distance means the star is intrinsically less luminous than earlier models assumed, which in turn implies it is less massive and younger. Studies using Gaia's data have produced age estimates more commonly in the range of 12 to 13.7 billion years. The paradox is fully resolved. The star is not older than the universe. It is simply very, very old. What makes this story scientifically important is not the paradox itself, but how it was resolved. Astronomy does not work by discarding established physics whenever a measurement appears inconsistent. It works by refining measurements and checking assumptions. HD 140283 became a benchmark case for stellar dating techniques precisely because it sat at the edge of what the models could handle. It forced astronomers to examine every source of uncertainty: distance, chemical composition, model parameters, and improve them systematically. The result was not only a better age estimate for this one star, but better methods for dating other ancient stars across the galaxy. HD 140283 also provides direct evidence about the Milky Way's earliest history. It likely formed within a few 100 million years after the Big Bang, during an era when the first generation of stars called Population 3 stars had already lived, exploded, and seeded space with the first heavy elements. Those Population 3 stars are now extinct. They burned fast and died young. HD 140283 belongs to the second generation, formed from gas enriched by those earlier explosions. That makes it one of the oldest surviving objects we can study directly. It is a relic, a window into conditions in the early universe that no longer exist. The star's motion through the galaxy also tells a story. Its high velocity and elongated orbit suggest it formed in a smaller dwarf galaxy that was later absorbed by the Milky Way billions of years ago. The star retains the orbital signature of that ancient collision. It is not a permanent resident of our stellar neighborhood. It is passing through, on a trajectory that will eventually carry it back out to the galactic halo. Looking forward, the precision of stellar age dating will continue to improve. Gaia's ongoing data releases are providing parallax measurements accurate to within fractions of a percent for millions of stars. Combined with advances in stellar modeling and spectroscopic analysis, astronomers will be able to identify and date more ancient stars with far greater confidence than was possible even a decade ago. HD 140283 may not remain the single oldest known star indefinitely. Other candidates exist, and future surveys may uncover stars that formed even earlier. But it will remain valuable because it is nearby, bright, and accessible for detailed study. It serves as one of the clearest test cases for understanding how the oldest stellar populations evolved and how to measure their ages accurately. The importance of HD 140283 is not that it breaks cosmology. It is that it anchors our understanding of the universe's earliest epochs. It is a reminder that some objects formed near the dawn of cosmic time are still here, moving quietly through the galaxy, carrying information about an era we can study in no other way. The paradox was resolved not by rewriting the timeline of the universe, but by improving the precision of our measurements and respecting the uncertainties inherent in working at the limits of observation.